Hello guys, today in this video we are going to discuss about the charge flow in the PN junction. Okay, or you can as you can see how the energy band diagram, what happens to the structure of the energy band diagram for different bias in a PN junction. As we know, in thermal equilibrium, when there is no voltage given to the PN junction, and what happens in the reverse applied bias when you apply your reverse bias. Okay, and then what happens when the PN junction is forward biased. So what happens to the change, what happens to the energy band diagram? That is the objective of this video here we're going to discuss. And knowing this, we can actually discuss the qualitative description of the charge flow in a PN junction. So as you can see in this particular kind of animation, you can see, so initially you can see the space charge width. Just let us see one variable and how it changes with like no voltage and reverse biased voltage, and then forward biased voltage. Okay, so now you can see the space charge width. Okay, when there is a voltage given VA, so when the voltage given is VA, a forward bias voltage, you can see forward bias, we know that the positive terminal of the battery is connected to the P region, and the negative terminal of the battery connected to N region. So you can see the space charge width decreases because of the diffusion force of the electrons and holes from the from the N region, and the P region will increase. As a result, the space charge width here as shown as W here, W as the space charge width will decrease, right? And then the flow of the majority charge carrier from the N region to the P region will occur, right? So this is what we saw in VA, which is the applied voltage for the forward bias, right? And when it is VR, you can see when it is VR. Okay, just see when it is VER, which is written for the reverse bias. Okay, or a reverse voltage given. Reverse bias means what? When the this the terminal, the P region is connected to the negative terminal, and N region is connected to the positive terminal. So the space charge width, you can see this space charge width increases, that is maximum at VR actually. Okay, for a particular reverse biased voltage given. And you can see the other variable here, you can see, is electric field. What happens to the electric field? The electric field, when we said electric field in the depletion region or the space charge region, you can see the electric field was small in VA, then it is little bigger when for thermal equilibrium, and then it is maximum or more in VR. Okay, when the biased is reversed, right? Biasing is reversed. So now here you can see the energy band diagram. Accordingly, you can see the energy band diagram. What happens to the energy band diagram? You can see the EVBI, which is thermal equilibrium value, EVBI, that gives you the built-in potential barrier in terms of energy. If you want to write, then you multiply this small e with the built-in potential barrier. That gives you the gap in the, or the bending of the conduction band, valence band, and the intrinsic Fermi level, right? Now, when there is a forward biased, as we said, the space charge width will decrease, and the gap or the bending becomes here E VBI minus VA, where this VA is the applied voltage and forward bias given. And if you will give a reverse bias, then it becomes E, this becomes VBI plus VR, right? So you can see the bending is more here in reverse bias. So let us see one by one, so things will be more clearer to it. So let us now move to this particular, you can see this is for thermal equilibrium. The PN junction is in thermal equilibrium. So thermal equilibrium, we have the space charge width. We have already calculated what is the space charge width considering abrupt boundary xn and xp, and this is the electric field in the space charge region, that also we have calculated. Now you can see here As you will see here, you can see the p region and the n region here. Thermal equilibrium, the average energy of the electrons throughout, okay, will be the same. So here you can see this EFP is the Fermi energy level in the p side, and EFN is the Fermi energy level in the n side. Okay, it is constant throughout because we said it is in equilibrium, thermal equilibrium. Okay, so equilibrium. Now initially what happened, you can see the Fermi energy level here, okay, in the p region and n region were different. Of course, p type and n type material, if you'll see, the Fermi energy level are different. So here if I'll just draw it, then individually, then we can see, okay, suppose for p region, what we got, p region, you got your EC here, okay, and then you have the EV, okay, and the Fermi energy level here is close to your valence band. So this one was your EFP. Now in n region, this also we have already discussed, you can refer to the previous videos. EC, and then you have EV. Okay, in the thermal equilibrium, when you calculated the built-in potential barrier, we did it. So this is your EFN. Now when you will combine this, you can see the EFP and EFN, okay, they will be in equilibrium. Okay, they will be in equilibrium, means have a unique value, okay, will be constant throughout. So this is what we got here. Okay, now, so here this is the potential drop we said, or the energy drop or the energy gap, you can see that we have already discussed. Now what will happen if you will give a reverse applied bias? So reverse, as we said, this p region is connected to the negative terminal, n region or n side is connected to the positive terminal of the battery or the cell, you can see. So that the depletion width, you can see the space charge region will increase. So space charge region W increases here, right? As more number of space charge will be accumulated here at the metallurgical junction, the electric field will be more here. Okay, and the same can be shown in the form of a energy band diagram. So in energy, if we'll show the energy band diagram, you can see if you are giving a a reverse applied bias, then you can see the depletion width will be more, and the bending, okay, the gap between the EC of the P and EC of the N region will be more. By what amount it will increase? E times VR amount. So it initially it was EVI, now you got E times VR, right? So it will increase, right? Now you can see why this happens when you are when you are applying a reverse bias. What will happen when you are applying a reverse bias? You can see here we will discuss more related to the the minority and majority charge carriers. I'm just uh, telling you what we are going to take actually. Here in the n region, what you got in the n region, you have the majority charge carriers, those are electrons, right? And in the p region you have majority charge carriers, which are holes. Now when you are giving a reverse applied bias, actually what you are doing, there are some holes here, okay, there are some holes here in the n region, which are the minority charge carriers. So now these minority charge carriers are moving in this direction. Okay, we in this moving in this direction. Similarly, there are minority electrons over here in the p region, and they will be moved further into this region, right? So the minority charge carrier flow. Okay, but what will happen to the majority charge carrier? Majority charge carrier will be dragged toward these terminals, right? So towards these terminals, like your holes and your electrons over in this case, right? So the depletion width actually increases. So this is what is shown. So of course the distribution function will change, right? The distribution function will change. If the distribution function will change, okay, then the Fermi energy level will also change. So distribution function means the concentration of a majority charge carriers, or the majority charge carrier electrons in n region and holes in the p region will change, and definitely that will change the overall energy or average energy, right, in the p and n type material. So you can see there is a shift in the Fermi energy level. Earlier, like in previously it was same, it was constant throughout. You can see EFP and EFN in thermal equilibrium. But now what you got, you just connected to the reverse voltage. So you can see there is a drop in the concentration of the electron. As a result, the Fermi energy level will come down, and here there is a drop in the whole concentration in the p region as well. So drop in holes means what? A relatively high electron, that way you can consider. So here you can see Fermi energy level goes up, right? So electron concentration drops, so the average energy of the electron will drop, so the distribution will be affected, so it goes down, and here it goes up, right? This is what is observed here. You can see that the drop in the Fermi energy level in the n side, and the rise in the Fermi energy level in the p side. So this creates the non-equilibrium, okay, in the Fermi energy level. And here you got the, this is the energy gap, okay, the same. And the space charge width also, you can see that increases here. Okay, now we will do the opposite. What we will do, we will use a Va, okay. So forward applied bias with a value Va applied bias, okay. Then what will happen, the space charge width will decrease because of the diffusion force of the electrons and diffusion force of the holes. Okay, so the electric field induced or electric field in the space charge region will also decrease. So you can see this is nothing but a measure of what? Measure of the energy, or the potential that is required for the electrons to move from the conduction band of the n side to move to the p side. Okay, so this value will also decrease. Now what we got, as we said, this negative terminal is connected to the n region. Okay, so electron will have higher energy. Okay, so the concentration of electron, that way you can say it is like going up. Okay, so you can see there is a elevation in the average energy of the electron, so the distribution will be affected and the Fermi energy level will rise. And similarly here, the whole concentration here in this case, whole concentration, you can see now this whole concentration is connected to what? The positive terminal. So the concentration of holes will increase. So concentration of holes will increase means what? Relatively the average energy of the electrons will decrease. Okay, so that way if you'll see, then the drop in the Fermi energy level, or you can say this way, that the Fermi energy level will move more close to the valence band as the concentration of the holes will increase. Here that way also you can see, as the concentration of electron will increase because n region is connected to the negative terminal, so the Fermi energy level will move closer to the conduction band here. And this here in this case, Fermi energy will come closer to the valence band as the whole concentration will increase. So this way also you can think, right? So this is the energy band diagram. Okay, this will be the energy band diagram of a forward biased PN junction. So this is important to understand. Okay, so all these three types of biasing and what happens to the to the structure of the energy band diagram. So we said three things actually. When it is in thermal equilibrium, Fermi energy level will be constant throughout, from which we have already determined the built-in potential barrier. The second one we discussed, when it is reverse biased, we said n is connected to the positive terminal and p is connected to the negative terminal. So here you can see the electron concentration falls. When the electron concentration falls, okay, so the distance between ec and ef, okay, will increase. That's why it's going down. Okay, the same way here it goes up, right? Because we said the concentration of holes will here in this case will decrease. Okay, so relatively the electron concentration is increasing that way, right? So it's going up. So this is what we got. Okay, will be reflected here, the in the bending, in the space charge width, in the electric field that will be induced in the space charge region, right? So this will be the structure. And finally this one, where we said if you are giving a forward bias voltage, then you can see the space charge width will decrease, the induced electric field in the space charge region will decrease, and you can see the gap here. As this is connected to the negative terminal, n region is connected to the negative terminal, electron concentration will increase. Electron concentration will increase means Fermi energy level will be closer to the conduction band. And the same thing happens here. As the whole concentration increases, the Fermi energy level in the p region moves closer to the valence band. Okay, so based on this concept, we will discuss what are the majority charge carriers, minority charge carriers in both p and n region, and then we will consider the ideal current voltage relationship, and we will be able to establish a relationship between the majority and the minority carrier concentrations in the n region or in the p region. Okay, so we will continue this in the next class. Thank you.